Hello everyone. It is Fajer Alelaj, PhD researcher at Newcastle University. Today I will talking about the solving power quality issues by the hybrid distribution transformer. So in our presentation, I will discuss the introduction, which will be about the power quality issues and the hybrid transformer, also the proposed hybrid transformer, the design of the proposed converter, the control of the proposed hybrid transformer, the simulation, and finally the conclusion that our finding results. To start with the introductions, so up here I'm coming up with the proposing of hybrid transformers. So we know that the increasing penetration of electrical vehicles charging system and installing renewable energy system will create a power equality issues. So as such as the voltage variation in the grid, a voltage sag, and as well harmonic distortion and a weak power factor. As we know that the reasons of having the voltage variation in the grid is coming from load variation, is coming from the energy, renewable energy resources with weather disturbance, and also a switching impact. So the most serious problem that we have in the power systems was the the voltage sag and voltage swell, and this is the issues that challenging a lot of industrial customers in the distribution system. So as you see here, this is the distribution transformer, the convention one. As we know that the convention distribution transformer was a cheap, reliable, extremely efficient, but cannot handle unwanted actions such as the voltage sag and voltage swell. So there is like a common technique that was used to regulate the voltage sag and swell issues in the distribution network, such as on-load tap changers, dynamic voltage restorer, rider-through voltage compensator, dynamic sag corrector, and a hybrid distribution transformer. So each technique have like disadvantages. As example, on-load tap changers, strict range of output voltage compensator, stepwise alteration, also by dynamic of a voltage regulation. We talk about now dynamic sag corrector and the rider through voltage compensators. They can mitigate only for the sag condition. And about the dynamic voltage restorer, it's have high power rating and make the DVR to be expensive. So the hybrid distribution transformer is a combination between the conventional distribution transformer and the power electronics converter, which has the ability for the regulation during using the power electronics converter. And also the hybrid distribution transformer, it's helped to reduce the impact of the power system. So in generally, as you see here on the right side of the slide, we have like two structures of the hybrid transformer. The first method, which would be connect the converter on the primary side. The primary side is the high voltage side. It has advantages like a low current and consuming a high voltage power electronics transistor. And the second one, which would be connect the converter on the secondary side, which would be the low voltage side, and have also disadvantages of that connection, that passing high current resulting to the high power losses. In my proposed hybrid transformer, I prefer to connect the proposed converter on the primary side. I prefer to deal with high voltage and low current than to deal with high current and low voltage. So as you see here in this slide, this is the proposed of the hybrid transformer. As you see here, this is the proposed back-to-back, which is located at the primary side of the distribution transformer. So the back-to-back is composed of active front rectifier and MMC, which is the modular multilevel converter. This converter was used to regulate the voltage at any case like voltage sag and voltage swell. Sorry. So the proposed converter was integrated in that area. As I said previously, I prefer to deal with low current and high voltage. So I was used active front rectifier to regulate the voltage of the DC link. Also, I use that one because it helps to help the back-to-back, the proposed back-to-back to be reduced of the volume and also the cost of the converter. So as we know that the MMC is one of the multi-cells converters family, so it can be operated from medium voltage to the high voltage, and also can operate it and in high power conversions because of the high modularity and the high voltage scalability, and also because of the lower total harmonic distortion. So as you see here, this is the proposed back-to-back, which is the active front rectifier and the MMC. So regarding the MMC, the submodules, it was the half bridge. It was a simple. The half bridge, as we know, that is simple, and the control was simple also. As the control, as in the standard process, one of the devices will be on, and the other will be off. But there is advantages of using the half bridge. The advantage of that one is because of it having lower losses, so it will have higher efficiency. So now we talk about the design of the proposed converters. So the design of the MMC will be based on a capacitor's values of the submodules, inductor size, and the number of the submodules. So the number of submodules is determined by dividing the DC link voltage by the desired voltage of the submodules capacitor. As you see here, this is the equation of the submodules, of the capacitor value of the submodules. So the submodules capacitor will be depending on the maximum capacitor voltage ripple, current ripple, and the submodules voltage capacity. As you see here, this is the equation will be depending on fundamental angular frequency, also the DC, which is the DC voltage, the number of the submodules, and that one is the function of axis, voltage axis. So this is the modulation index, and that one is the power factor angle. So the second things will be designed the arm inductor. So this is the equations of the arm inductors. So the main function of the arm inductance is to suppressing the second order harmonic component of the circulating current, and also to limit the fault current in the event of the DC short circuit fault. So the equation of the arm inductance will be depending on also the angular frequency, will be depending on the voltage of the capacitor, the value of the capacitor, the apparent power, also the peak RMS value. So the design of the rectifier is based on the capacitor value of the DC link. So as you see here, this is the equations of determine the value of the capacitor. So it will be depending also on the ripple of the voltage. This is the voltage of the DC, the switching frequency, and also the load resistor. So the control of a proposed hybrid transformer will be divided in two parts. So the first part was to control the active front rectifier, which will be responsible for regulating the DC voltage. The desired voltage of the rectifier was depending on the supply voltage. So as you see here, that there are three equations. This three equation was based on the VS, which is the supply voltage. These three equations will be for each cases. For example, the normal case, which is the voltage supply will be 11 kV. The sag case will be the supply voltage 10 kV. The swell case, which would be also the supply voltage 12 kV. This equation in order to determine the voltage of the DC link. So you see this ratio is a 3/2. This is is it the ratio of between the desired DC link and the desired output AC voltage, and was be selected. I was starting with a normal case. So the normal case, we have like 90% of the power will go directly from the grid to the load side through the distribution transformer, and the 10% of that one will just go through to the system, and then through to the converter. After that one will go through the distribution transformer. So, and that one is 1100. That values is representing the 10% of the normal voltage, which is coming from the grid. So the sag condition, on the sag condition, the sag, it's mean that the voltage, the supply voltage will decrease under the normal voltage. So that's one, the converter will have the responsible to compensate to reach the required voltage. So therefore, there are a positive part, which is that one, to be added to the normal equations, so that help the proposed back-to-back to compensate the output voltage. The second one, which is the swell case. So also the swell is mean that the voltage, the supply voltage will be increased and it will be above the normal voltage. And that one should be the converters had to compensate and able to be compensate. And there is a negative part will be added to the normal case. So it helps also, it helps the proposed converters to decrease the value and reach the required values of the output. The second part of the control, it was to control the MMC, as we know that the MMC was responsible for the balancing the voltage through the submodules and regulating the AC output voltage. So that this control will be based on the DQ reference. So as you see here, this is the figure of the control. So there is like consisting of two control loops. There is outer loop, which is the voltage control, while the inner loop will be the current control. And this is the peak desired, which is 340. This is the desired output voltage. So there are many different pulse width modulation technique was used to balance the voltage on the submodules. So the proposed technique was that I use it in this proposed hybrid transformers, the proposed MMC was the phase disposition. Because it's higher, because I choose that, I select this, or I choose this technique because it has a higher capacitor voltage self-balancing capability and also less harmonic distortion for the output voltage. So I will explain the phase disposition PWM. So in my system, I have like two submodules per arms. If the current on the arms is even was upper or lower is a positive, and the submodules will be it will be positive, and the submodules of the arms will be on. So that's when the capacitor will be charging. So if the current in the arms, so even so as it was upper or lower, was a negative, so the submodules is on. So the capacitor will be discharging. So if the submodules was off, so the capacitor will remain constant. So the submodules of a submodule voltage will also will be sorted in descending order. So the required number of the working submodules are in the upper arm plus the lower arm equal to 2. And the voltage of each submodule should be regulated to the VDC over 2. So, so the working submodules in each arm is determined by 3 levels, 3 voltage levels. So the first level was if all the submodules of the upper arm will be on and the lower arm will be off. So the numbers will be n uppers is equal to and n lower will be 0. The second level, which if there is one submodules will be on in each arms, so then n upper equal to n lower equal to 1. And the last level, which if all the uppers will be off and the lower submodules will be on, so the n lowers will be equal to 2. So this part is the simulation of the proposed hybrid transformer. So as we know that it will be divided into cases. So this is the first case, which is the normal case and sag case and the swell case. And this is the parameters that will be in the proposed converter. So the voltage supply is 11 kV. The submodule's voltage will be 1000 volts. Load resistor will be 100 ohm. Also, the submodule's capacitor will be 1.9 milli, and the arm inductance will be 0.01 milli. So this is the first simulation. So as you see here, from 0 second to the 1 second, this is the normal case, which will be the voltage supply is 11 kV and the voltage DC will be 1350 volts. And here on the second period, which will be from like 1 second to 0.2 second, this is the sag condition. So the voltage supply will be 10. As you see here at the beginning of the period, like it's having like the voltage is becoming lower, then the system is trying to fix and to regulate the output voltage. Also, the DC voltages was around 2570, and the rest of the period, it was a swell case, which was the voltage was around the voltage supplied was 12 kV, and the VDC was around 122. As you see here, are the same. It's having like the voltage will be increased, and then it's tried to regulate again. The second simulation, it was unbalanced phasor voltage. That means that one of the phases will be the load resistor will be different than the others. So in this case, I choose that phase A will be 50 ohm, while the rest of the submodules will be, the rest of the load will be 100 ohm. So as you see here, that the output voltage will remain at 340, which is the required. So the other test, it was when I change all the submodules, all the loads will be 50 ohm instead of 100. As you see here, also the system reached the required output voltage, and that one is representing the current. The current was affected and was increased according to the Ohm's law. The last one was when I changed the load resistor from 100 to be 150 to represent the swell case. So in this case, also the system reached the output, the required of the output voltage, and the current is affected because of the Ohm's law. It was decreased. So to be concluded that the hybrid transformer was simulated under different cases, and also the result that proved that hybrid transformer has the ability to compensate for the output voltage load with 10%. So if anyone have questions.